So hello, how y'all doing? I apologize for starting 45 seconds late, but you know, I'm a rebel. So I'm going to break all protocol and take a picture, because I don't see anyone from my company taking a picture, and so I thought I should take one. So just to prove how many people are here. There we go. Thank you. Yeah. Who flipped me off? I saw that. Oh, okay. They said I was number one. So for those who didn't read the schedule, my name's Guy Royce, and this is Machine Learning for Gamers, Dungeon Forecasts, and Dragon Regressions. And what we're going to do today is I'm going to talk about a little bit of the what and, well, mostly the what of machine learning. What is it and what can you do with it? What kinds of problems can it solve? I'm not going to get into the nitty-gritty detail of, well, when you've got this exact problem and then you use this formula with this algorithm and then you set this setting. It's just higher level talk than that. But before I get into that, I'm a developer evangelist with Nexosis, and I'm not going to make this a role product-y talk. This isn't about our product, but we do have a product. We'd like you to check it out. It's a machine learning API. And they pay me to come out to events like this so that I can say that. So this is some people at our company. And Nexosis is a company full of developers. So our CEO is a developer, our CTO is a developer, our data scientist writing code, our head of marketing is the one that does all the CSS for our website, and he's doing the JavaScript. So almost everyone in the company is a developer of some sort. And our objective is to make machine learning available for everyone. And I am going to tell a story about how our company formed, not because I want to plug my company a ton, but because I think it's actually kind of a cool story. So how many of you guys play Counter-Strike? Right? Actually, I don't play Counter-Strike, but I'm glad you guys do. So the two guys on the bottom of this picture here is our CTO and their CEO. And our CEO used to play Counter-Strike professionally, or competitively. And so he decided to find people that were cheating using machine learning. And so the two of them got together and they took the data of all the banned players, and they took the data for all the top 1,000 players and built a model, and then was able to detect who was cheating using this model. And so they did a talk at DerbyCon and made a YouTube video and threw it up on YouTube. And they didn't think much about it after that. 2 years later, they get a call from a Pepsi distributor in Columbus, Ohio, saying, hey, I saw your video on YouTube, and I was wondering if you could do this sort of stuff for my business. I'm like, yeah, sure, we can do that. Well, who do I make the check out to? I'm like, what? Oh, crap, we need to get a company name. And that's why our company's called Nexosis. So, but we're all very developer focused. And I mean, even at the very beginning, it was a developer at a conference doing something cool with machine learning. So before we get into all that, though, I do want to put one big qualification here. What does this stand for?
I am not a data scientist.
I am not a data scientist. I'm a developer. Up until about 6 months ago, I was working in consulting, building mobile apps. I hadn't done very much with machine learning. So I'm not an expert. I know how to use our product really well. And I know fundamentals of machine learning, which I'm going to share today. But if you've got detailed questions about why I would pick one algorithm over another, or what this setting does, or even really deep math questions, I'm not going to be able to answer them. So, so don't ask. Or if you do ask, I can point you to one of our data scientists that's at our booth, and they can answer it for you. That's just not my role. It's not my area of expertise yet. I mean, how many here are developers, right? There's like one person that didn't raise their hand. And so let me ask this, as a developer. In the last 15 years, what's the most advanced math you've used? A little bit of trig maybe, right? And that's up there, right? I haven't used anything beyond basic algebra since 1994. And so I'm not mathy. And a lot of us have had advanced math, but we haven't looked at our linear algebra book since 1994. And so I'm not going to get into the mathiness of it. I'm instead going to talk about how machine learning is like Dungeons and Dragons. So remember the first time you heard about D&D? Well, for some of us that might be, we might have been 8. But it sort of has this effect, right? If you look at this picture, you know, it's like there's a lot of weird dice there. What do they do, right? You got the, you know, I see a rock, paper, scissors, lizard, Spock die. I see some funny shaped dies. There's that red one that looks kind of like a top in there. There's just all these weird dice. And machine learning's like that. It's got all this weird jargon, all these weird tools. Gaming's got all this weird jargon. You know, how many hit dice do you have? What'd the paladin say? Oh, what was his alignment? Well, he's supposed to be lawful good, but, you know. But Ken's playing the paladin, and so he's going to be lawful evil and think he's lawful good. Or what's the color of that dragon? Well, why does the color of the dragon matter, right? There's all this jargon in gaming, and there's all this jargon in machine learning, encoding and imputation and aggregation, and they have specific meanings. And what is regression and classification and clustering and supervised learning and unsupervised learning. And it's just a lot of words. And they both have a lot of excitement around them. So when you first came to Dungeons and Dragons, everyone else was really excited. And, but you didn't really understand it. But it's like everyone's excited. I should probably check this out. That's kind of what machine learning is like right now, right? Everyone's getting excited about machine learning, but a lot of us are looking at it and saying, well, I need to check this out. And you know, that you're vaguely concerned that you're missing something. And so this is the first step, if that's you, in explaining what machine learning is. So what is machine learning? I'm not asking, I'm pausing. It's rhetorical, don't worry. So I like to say that machine learning is math at scale. So a lot of what we do with machine learning is math that we've known how to do for decades, some of it going back to the 50s, some of it going back way further than that, going back centuries, that we can actually scale up because we have enough GPUs to actually figure out that 1,500 dimensional linear algebra problem. Or I don't know how many dimensions you want, right? We got a lot of processor capability. We can take that a lot further than humans can take it. And up until recently, we haven't had enough microprocessor power, enough transistors to actually make that possible. So machine learning is enabling us to do math that we figured out a long time ago, statistical analyses that we can now actually do. And so that's why everyone's excited about it now, because we can do it. A lot of machine learning is about taking a lot of examples of things and then building models that reflect those examples. And then using those to make predictions. So you know, your big simple, the super simple 3-step process for machine learning is you gather a bunch of data. These are a bunch of examples. So it'd be examples of, say, like prices of houses and all their features. You know, the square footage and this kind of stuff. And then we use all those examples to build a model, and then we can predict how much a house is worth based on those features. And once we build that model, then well, we can make predictions. So it's to gather data, build a model, make predictions. Now this is a gross simplification, right? But that's the basic concept of it. And when we gather our data, you know, there's a little bit we got to do there. We got to know more than just throw a big pile of data at it. We have to figure out what our target is. We need to figure out what our features are. We have some encoding we need to do for data that's not numeric because we're doing math. We've got to impute values that aren't there because we can't do math on nulls. And so let's talk about some of those terms. The target is the thing you want to predict. A feature is a thing that affects the thing you want to predict. It's not actually a hard idea. This is all tabular data, but just one of your columns is your target. And when you're gathering your data, you need to have lots of examples with features that go to that target. Encoding is how we take data that's not a number and make it a number so that we can do computation against it. So we can shove it into that linear algebra problem. Or we can shove it into our neural network and have it actually propagate math through that network and get results out. And imputation is how we figure out those nulls. Incidentally, this is a codex. That's why I picked that image. So I'm trying to go with the D&D theme, right? Encoding is actually not that complicated. I got a couple simple examples of encoding here. The first one's a Boolean. Encoding a Boolean is something we've been doing in computer science since, well, the beginning. You know, here we've got an example where we say, is it a goblinoid or not? If it's yes, that'd be a true, so we put a 1. If it's false or no, we put a 0. We can also do one-hot encoding to encode our data. And this is where we take, we've got a string, like in this case, the color of a dragon. Is that a black dragon, a blue dragon, green dragon, a red dragon, or a white dragon? Because in Dungeons & Dragons, that matters a lot. And to convert them to numbers, we'll create a column for each of the types of dragons that we have, and we'll put a 1 in, the one that matches, and we'll put a 0 in the rest. So it's kind of like creating a whole series of Booleans that says, is this a black dragon, yes or no? Is this a blue dragon, yes or no? Is this a green dragon, yes or no? And so these are some basic encoding techniques you can use to get your data into a numeric format. Following so far? Good, lots of head nods. I haven't seen anyone's heads be blown yet. This is actually, this is an intro level kind of thing here. So once we've gathered that data and we've encoded it and filled all our gaps using imputation, we can build our model. And the way you build a model is you pick an algorithm, and then you take some of the data to train it and some of the data to test it. So here's a list of some algorithms that I copied off of our website that our API supports. And there's lots of them, and you could pick them for all sorts of reasons. And honestly, I don't know why I would pick one algorithm over another, because I'm not a data scientist. I'm not deep in that. I haven't gotten that deep yet. But these are different algorithms you can select. You pick one. And then you take your data, and you use it to train that algorithm. So these are all the examples. So the algorithm will do this math, and it will use these examples and come up with weights for outputs to make your predictions. And some of that data is used to train it, usually about, I think usually about 80% of it. You can vary your test train ratios and for what you're trying to do, and there's lots of techniques for this. And then about 20% of it you'd use for validating that the trained model is accurate. So you don't want to take all that data to train it, because if you do that, you'll get a model that's perfectly matches your example data, but doesn't necessarily match reality. Once you've done this, you'll test out your model, and it'll probably suck. And so you'll go back and you'll look at your data. So maybe my examples aren't very balanced. Maybe I've got too many examples of one type of dragon, but not enough examples of other types of dragons. Or maybe I just don't have a good representative. I don't have all the types fairly represented in there at all. So maybe blue dragons aren't represented in my data, or there's like one record. And so it can't make good predictions about blue dragons. And so I go in and I massage my data. And some of the features I might have picked might not have had a bearing on the thing I'm trying to predict. So, so maybe I need to take it out. And maybe I'm missing a feature. Maybe there's an important aspect to a dragon that would predict something about it that I miss, and so I need to add extra data. So I'm going through this process of getting my data right and then building models. Maybe I picked the wrong algorithm, and so I need to select another algorithm. You cycle through this lots of times. And eventually, you'll get a model that's good enough for your purpose. Now, if you're doing, you're analyzing echocardiograms to see whether someone's going to have a heart attack or not, then your thresholds are going to be higher, and you're probably going to be a lot pickier about how accurate that model is. If you're just trying to figure out what's the value of someone's home on Zillow, plus or minus a couple $1,000s is probably okay. If you're doing Dungeons & Dragons, it doesn't matter. So once you have this model and you're happy with it, then you can use it to make predictions. And making predictions is simply a matter of providing the features that affect the target and then getting the target. That's pretty much the general idea behind machine learning. So if you do nothing about machine learning, you now know that you need to gather data, build a model, fix your data, build a model, make a change, build a model, and do that a lot of times, and then eventually you'll get a model that you like and you can use to make predictions. So that's fine. What kinds of things can I predict? What kinds of problems can I solve? Right? So this is all pretty abstract. Well, I'm going to talk about 5 of them today. I think in the abstract I said I was going to talk about 6, but I nixed one. And So I'm going to talk about regression, classification, anomaly detection, forecasting, and impact analysis. We're going to talk about regression first. And so the problem we're going to solve with regression is we want to know how much a dragon's hoard should be worth based on the age of that dragon, the color of that dragon, and how many hit points that dragon has. This is important D&D stuff. Because, you know, if you hear rumors as a player, or I'm sorry, as a character, because you're role-playing, right? About the red dragon up on, you know, White Peak Mountain, and everyone says, yeah, it's you know, he's really tough, and he's super old, then that means I should go kill that dragon, because I'm going to get a crap ton of gold. You want to know that, right? It's important information for hardcore role players. So regression problems, that's a great example of a regression problem. I'm trying to predict a numeric value off of a bunch of examples. In this case, I would have a bunch of example dragons, and then I would predict a feature of those dragons. So a little bit about dragons. So how many of you play Dungeons & Dragons? Thank God. I gave this talk at a school the first time with like 13 engineering students. Only 2 of them were programmers. None of them had played Dungeons & Dragons. It was the worst experience of my life. So dragons have, for those of you who are Dungeons & Dragons aficionados like me, know that dragons have an age, and I used 5th edition rules. It was great making the slides because I got to get my D&D books out at work. And I never get to do that, right? Actually, I downloaded the PDFs off the internet. But they got an age. You got wormling, young, adult, and ancient. So, you know, the older a dragon is, the bigger and more badass it is. But also, the more time it's had to accumulate treasure. So age seems like something that would affect how big a dragon's hoard should be. The color of the dragon talks about, actually says a lot about a dragon. You've got your chromatic dragons on the left there, the blue, black, green, red, and white. And you've got your metallic dragons, and they're very metal. And you get your brass, your bronze, your copper, your gold, and your silver. And the different colors of dragons have different strengths. So red dragons are more powerful than white dragons. And you know, white dragons are kind of dumb, and the blue dragons are fairly intelligent. All the metallic dragons are good aligned, and all the chromatic dragons are evilly aligned. And so, you know, if someone's got an evil alignment, they're probably more likely to steal gold from people, right? Whereas the good dragons, they probably don't go to the town and eat all the people and take their gold. And the relative power levels are going to have a lot to do with how much gold they can get. Same for hit points. This is how much, you know, damage that a dragon can soak up before it's dead. And so if a dragon's got a lot of hit points, it's harder to kill. It's probably eaten more adventurers and has more gold. So, and then there's the hoard value. You know, this is just the total gold piece value of all the things the dragon has. That's the thing we care about, right? And that's actually the target in our scenario. So here's our sample data. We would probably have several hundred or maybe 1,000 or so sample dragons here. It depends on how many features you have. I mean, it's not a precise thing. But I'm just going to show a few here. You see we got the age of the dragon as a column in our data. We got the color, we got their hit points, and we got a hoard value. And so age, color, and hit points are our features, and our hoard value is the target. And so we go through our test train thing, and we select randomly the dragons, sample dragons we're going to use to train our model. We select the ones we're going to test with. We test it, and hooray! After doing that 50 times, we got a good model. So that's the data that we need to put into our model to predict things about dragons. So here's the questions we can ask. I've been talking about hoard value. But you can actually use regression to predict any numeric value in that set. You got to build a different model each time for that. But you can build a model using this data that predicts the hoard value of a dragon based on its age, color, and hit points. Or you could predict how many hit points a dragon has based on its hoard value, its color, and its age. Those are both viable scenarios for regression with this sample data. And that's kind of useful. Actually, it's totally not useful at all. But an interesting question is why can't I predict the color? Or why can't I predict the age of the dragon? Right? I mean, what's that?
Not numeric input originally.
Yeah, they're not numeric input. Yeah. Can I say, what color is this dragon based on its hoard, hit points, and age? Can I say, how old is this dragon based on its color, hit points, and hoard value? The answer is you can do that. It's just not a regression problem anymore. What you have is a classification problem. So classification is about predicting a class, a category, based on a set of data. And it works a lot like regression. You take a whole bunch of samples and you say, this is this class, and this sample here, example here, is that class, and you feed that all in and you build a model, but instead of predicting numbers, you're predicting a string, you're predicting a class. And what we're going to show here is we're going to do what I call literal classification. And we're going to predict, based on your 6 key attributes, strength, dex, con, intelligence, wisdom, and charisma, and the race you want to play, what would be the best class to choose? So we're literally classifying your abilities. So what's your guys' favorite D&D characters to play? What class? Druid. Druid or barbarian? What's that? Paladin? Okay. My favorite is the anti-paladin. There's lots of classes. I mean, I've got the ones listed here. Anti-paladin's not on the list because it's not part of the core rules. But every character's got 6 abilities, typically measured from a value of 3 to 18, although they can go higher than that or lower than that if you're truly pathetic. You've got a race. Are you an elf, a dwarf, a halfling? Are you dragonborn? I hate dragonborn, actually. They just break all my campaigns that I built 20 years ago because they weren't part of it. And this is just, it's the race of your character. And you got the class. That's your set of capabilities. Am I, a big, strong hill guy with a great sword? That'd be a barbarian. Am I a sneaky guy from the city? That'd probably be a rogue. Am I the bookish guy that lives in the tower and does weird arcane things? That's probably a wizard, maybe a warlock. I'd probably be more in the basement summoning demons if you're a warlock. Am I a fighter, a monk? What class do I play? So this is just like regression. Here we've got a bunch of training data. Here instead we've got all our abilities, and they're all numeric values. And we want to and we provide the class, or the race, sorry, and we want to predict the class. And so we provide lots of examples of characters that are suitable. Now you could create really bad data here, right? I could say, no, they're all 3s and they're a barbarian. That's not going to be useful data for our building our model. So you would take that data out. You want to provide example characters that are playable. And once we pick our test and train ratios and we build our model, then our question looks like this. We can say, well, I rolled a 14, 13, 15, 11, 9, and 15, and I want to play a half orc. So what class should I play? And sometimes some algorithms for classification will say, you should play a barbarian. You should play a barbarian, because I know you like that. Sometimes you'll get a score. So in this case here, we've got a score of 0.9184 for barbarian, and then slightly lower one for bard, because it's ironic that a half-orc would be a bard, and so on. And it would be really, 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 really tempting to think that these are percentages, but they're not. They're a score, and they're relative to each other. It's a lot like in an agile team space where you've got points, and you really, really want to say this team's points are the same as this team's points. That doesn't work because each team kind of has their own thing. Each model from a particular data set is going to have its own scoring. And it's going to be based on the algorithm as well. So it's just relative to each other. It's not necessarily a percentage. Now, these are in a very percentage range, and so it might suggest that, but that was so I could make this point. They're just a score. And you'll see this in anomaly detection as well. And so, because it's looking at a lot of examples, and it's kind of making a guess, you think about this is kind of what we do too, right? We'll look at your abilities and say, well, I've seen strong characters before, and they usually make good barbarians, especially as a half-orc, so you should probably consider a barbarian. And I'm reasonably sure of that. But, you know, your charisma is pretty high, and a bard's not implausible here. And so maybe a bard, maybe a cleric, and so you're sort of ranking them or scoring them. It's a little squishy, kind of like our brains work. You could also ask for the race. It's the same phenomenon. We're just looking for a different target. We're looking, well, if I want to play a cleric and I've got these stats, then I probably should be a dwarf. That's probably the most likely one. Or maybe an elf would be next, or whatever. But you can ask either of those questions off that same set of data. So far, so good? Cool. So the next one is anomaly detection. And what we're going to do here is we're going to say, based on 6 key abilities, and this isn't a perfect example, but based on 6 key abilities, a race and a class, is my character playable or not? Or what is the, maybe more say, what is the playability of my character? And so there's a couple of ways you can do anomaly detection. You can upload all valid data and find anomalous data that doesn't match that, or you can do a little bit of both. And this is a category of learning that's called unsupervised learning, because with anomaly detection, you're just uploading a bunch of data, building a model, and it's identifying, the act of building that model is, again, identify anomalous data and non-anomalous data. And it's just looking for patterns in the data, saying, most of the data here is like this, but this one is weird. And so you can do something similar with that with characters. And so I'm using exactly the same training data here. But instead of getting out of that a probability of what race or class I should play, I get an additional column for the playability. And so of all the ones that I've uploaded. And this playability is also a relative score. So we can see here that it's identified the half-orc barbarian as a 0.18, whereas the human fighter with a strength of 3 is a negative 0.02. So a positive playability would be something that's more playable. A negative playability would be something that's less playable. You could also do this as a classification problem. If you wanted, you could say, instead of having a playability score, you could just say this character is playable, this is not, and then you have a true class and a false class. And honestly, that'd probably be a better way to solve this problem, but I was stretching for examples at this point. So once you've got that model built, it's going to use all those examples that you gave it and the scores that it generated. Yes, sir?
Is it common to use anomaly detection to basically analyze your data that you use for regression and classification? You can get rid of that data?
I actually don't know that, but that sounds like a fantastic idea. Does anyone know the answer? I go back to that I'm not a data scientist. Yeah, I know that you can orchestrate these things and say, well, I'm going to use this data, this sort of machine learning problem to then give me data that I can feed into the next sort of machine learning problem. And I think anomaly detection would be a good category for that. I think that's a good idea, but I don't know the answer to the question.
And since this is unsupervised, how do you know if your model is good? You said you built it several times, but how do you test the validity of the model?
Yeah, so you get several scorings back on the quality of your model itself. The one we use the most at Nexosis is we'll measure the MACE, the error. It's an error score. I don't remember exactly what it stands for, or the MAPE, and it shows an error rate. You know, how of our test data, how much of it didn't do well. It's not exactly a percentage. It's just a score, but you can get a relative idea of how much it deviates from sort of the middle when you predict. But I'm not, like I said, I'm not a data scientist, so. You can also, part of that is just I built the model and then I used it and it just didn't do well. So that's part of that as well. So you've got some automated stuff that comes out of this, the process of building a model, but then you go and actually shove some results through it and it's like, this isn't identifying unplayable characters very well at all. Once you've built this model with the unsupervised data, you can use it to do further predictions by providing all of those fields and then getting It's saying this one is also anomalous. So a more practical example of anomaly detection would be like server logs. Not necessarily the text of the logs, but you've got, every minute I go out and I check the CPU utilization and the free disk space and all these metrics on a server. And I've got, days and days and days of examples of this checked every minute. And I can feed that into anomaly detection, and it will find all the weird ones. And then now I've got a model that knows how to find things that need my attention. And I can then continually feed in the new data as it happens and use that model to say, hey, this future thing is also weird, based on this historical period that we measured. Yes, sir?
So, did you guys actually build, this is actually built data that you have a model actually runs?
For these specific ones?
Yeah.
No, I didn't actually do them. They're just there to show the concept of,
My question is, like, did you use neural nets to do this? Is that what you use to generate the data?
For my actual slides?
Well,
Or just do you use a neural network for these sorts of problems?
you guys on
Yeah. Yeah, so we actually use a whole host of different algorithms. Some of them are neural nets, some of them are decision tree forests, and some of them are basic linear regressions, and we'll try lots of them.
So the data scientist guy, they didn't want to pick the algorithm,
Yeah.
how many layers and all that?
Yeah. We tend not to have, we don't do a lot of deep learning. Our neural networks tend to be a little bit shallow. The deep multi-layered neural networks are, they tend to be used for more, it's a heavier horsepower kind of thing. Yeah. That's the kind of stuff you're using to get all those funky images out of Google, for example. They're shoving all those pixels in, and then you're getting this weird thing out. They're using deep learning neural nets to do that. Yes? So it's basically positive and negative. It's positive and negative. So the question is what's the scale for the playability? And it's a lot like the classification where it's meaningful within itself. So, but positive is better, negative is worse. But in a particular data set for a particular model, your negative value could go from -1 to +1. It could go from -20 to +20. It's just a score that's meaningful within the context of that data set, but not across data sets. Now, I realized I talked about the slide and didn't show it. So I got about 12 minutes left, so I'm going to get into forecasting next. These are good questions. I've even answered some of them. So forecasting is predicting the future. You might have guessed that based on the name. The example we're going to do here is, and this is, I think, might be a legit product, so you should go out there and make it using our API. We're going to, totally, yeah. Not selling, yeah. So we're going to predict the number of encounters you can get through in an evening of gaming on your weekly game based on who's there and how long the session lasts. All right, this is actually useful, right? And so the data we have is the date. Did you have a question? I thought I saw your hand go up in my peripheral. Oh, you're scratching your ear. I see how you are. So we got the date, and for forecasting, date's real important because it tells you when it happened. We got a series of events, not so much examples, but a series of events through time, and we're going to do it weekly. So the date's important, and the data's full of data, right? It's got the month of the year, the day of the week, the hour of the day. It's got whether there's a holiday or not. There's all kinds of information crammed into that date. So it's a super valuable piece of information. You got which players have attended. Is Alice, Bob, Chuck, or Eve there? Now you've got how many hours we spent playing the game, and we got the number of encounters we got through. So this is all useful information. I'm sure all of us track that for all of our Dungeons & Dragons games, right? Does anyone track that? One. The data nerd back there. Of course, it'd be Clay. Yeah. Yeah. So here's what that data would look like. So we have our date there on the left. And you can see Christmas Day shows up on here on 12/25/2016. And then you've got who attended the game. So we got Alice, Bob, Chuck, and Eve. And you got yeses and nos for whether they're there or not. And those will get encoded as ones and zeros. You got how much time you spent in your game, and you got the number of encounters. And so what you do for forecasting, and I think this is really cool, is you provide all the features for the future. And then you get your target. So I'll show you here. So here we're going to say for December 12th, which was not in our data set, right? I ended it on February 5th. On February 12th, Alice, Bob, Chuck, and Eve will all be there. Because they all said they were going to be there. They haven't canceled yet. So I'm going to assume they're going to be there. And we're planning on playing for 4 hours. How many encounters will we get through? And what about the week after that? And what about the week after that when Eve said she wasn't going to be able to be there, but we scheduled a 6-hour game because we had the extra time? And so we can predict how many encounters are based on that. And we can play games with this. Like, we can say, well, what would happen if we played for 8 hours on the 26th? And we can change that and then do multiple scenarios of play. So we can do forecasting. This is great for games, but if you have a business, like say you have a pizza shop, and you want to predict what your sales are going to be, so you can say, how many people do I need to have on staff to do the sales? Being able to know if that promo you got going is going to affect sales or not is really useful. Hey, this promo is going to cost me $2,000. Is it going to make me $2,000? I can play games with forecasting. The other thing you can do here, of course, is you can also predict how long of a session do I need to have in order to get through 5 encounters. And what's funny here is that it'll pick up things like, in this data, it can figure out, for example, Bob talks too much at the game table. And so when Bob's there, the number of encounters we go through goes down. And so it'll figure out stuff like that. And you'll see, it's like, whenever Bob's not there, we seem to get more done. Damn it, Bob. And so this is forecasting. You just provide your knowable or reasonably knowable future scenarios to get a future value. You can also do predictions on both of these. So you could say, well, based on these people, how long does our session usually go? And then put that in, and then say, well, okay, how many encounters are we going to get through? So you can kind of daisy chain these as well, which is another trick you can do with forecasting. Impact analysis is similar to forecasting, but it measures, it does these predictions in the past against data we already have. And so I like to call it beforecasting. And so what we're going to do here is we're going to measure the impact of switching your campaign from Pathfinder to 5th edition. And then half the room leaves. So it's the same data, right? It's exactly the same data that we use for our forecasting. But we know that on January 1st, 2017, we switched to 5th edition because it was my New Year's resolution. And we want to see how does that impact how many encounters we get through. And so we can look here and provide that past date. We don't need to provide future values for our length or who's there because we know that. It already happened, right? But we can predict how many encounters should have happened versus how many actually happened and get an idea of what happened on that date that might have impacted that. So you end up with something that looks like this. So for January 1st, we got through 3 encounters after we had switched to 5th edition, but we expected to get through 5 encounters. And so that means Pathfinder, or the 5th edition has slowed us down. So the idea here is I know a thing happened, but the model doesn't know about it. The model's ignorant of this event. In the pizza shop example, the power went out. The model doesn't know that there was a power outage on that day. You want to see how it affected your sales. And so it's going to predict one kind of sales based on you having power. It's blissfully ignorant of the power situation, and you can make a comparison based on that power outage. It's a similar thing here. This model doesn't know that we switched from Pathfinder to 5th edition. So we can make a forecast in the past to see what should have happened based on past performance and compare it against what actually happened and then see the impact of that. The first time I did an impact analysis, I did a fun and ridiculous one, which was I was predicting the number of Bigfoot sightings over the course of, well, the 20th century. I had Bigfoot sighting data going from like 1900 to present. And it was the total number of Bigfoot sightings per month. And I measured the impact of the X-Files on the number of Bigfoot sightings. And so based on historical data, it was kind of a relatively low number. And so it predicted forward a relatively low number, but the actual values for Bigfoot sightings went up like this. It spiked dramatically because of the X-Files, because correlation is causation. So, but that's the kind of things impact analysis can let you do with time series data. I think it's super useful, and so you should check it out. And that's all I got, I think. Yeah, I think I finished with almost all my time used. Are there any questions? Yes, sir. I've got business cards right up here, and it's right here.
What character do you play?
Honestly, I like to play fighters. I like the straight-up character so I can focus on the role-playing, and then when it comes to combat time, I can just swing things and do damage. It's what it is secretly I like to pummel people, but you know it's an occupational hazard. Thanks a lot.